Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and today we're going to do some maths together. Hope that's all right. Joining me to moderate chat is current student whose name is Jake. Oh, sorry, Jake. I will say hi to Jake in chat if you like. If you'd like to join live chat, then you can do so at Vvox. There's a link on screen and in the YouTube description if you're watching live. If you're watching back afterwards, I guess you could put a comment on YouTube, but we might not see it. And I guess you could go to the Vvox, but we might not see that either in between. I've got a puzzle on the screen. It's a puzzle we're using for an activity at the Oxford Maths Festival, which is this weekend. I haven't mentioned this on the stream before because it's only really relevant if you're in Oxford. It's something we do for local people. We sort of take over a bit of a shopping centre and we do maths activities with people. Hello, who's in chat? Hi Johnny and Erin. Let's see, Jamie. How's it going? Going well, thank you, Jamie. Hi Miles. Hi Herb. And hi Oscar as well. I saw people in chat. Nice to see you all. We will do a poll in a minute for how's your day, but I'm going to give people a moment to get together. If you've seen this puzzle before with the lemons and the limes on the screen, let's read it out while people are joining. Let's just read the puzzle. You've got these three crates, which I have lovingly drawn using all of my artistic skill. These are the three crates. You can choose. Right, they've got labels on. We've got the right set of three labels that describes what's in the crates, but every label has been put on the wrong box. Each and every label is incorrect. They are all lies. What you can do is you can choose exactly one crate and take one random fruit from that crate. You do not get to look at the other fruit in that crate. And then you've got to fix everything. It's Jake, hey! There you go. You've got to fix everything. So your plan needs to be which box you're going to look in, and then what you do when you see that fruit. Right, cool. I can't remember if I've done this puzzle on the live stream before. If I have, then it's foreshadowing for doing this. Ooh, Ab's made a thing. We're moderating a chat message. Wait, hang on. No, okay. That's not a real thing. Right, thanks, Ab. Right, I'm going to review some of these, I think. There we go. Patricia says hello. I say hello to Patricia as well. Good, right, okay, let's start this going. I think Herb's either put the wrong link in or it's one of those incredible trolls. Where one of those incredible posts, because I clicked the link and I regretted clicking on it. Okay. Trying to get my head around chat as well. Like, chat is sometimes spooky the way it just sort of goes. Jake, people are asking questions to Jake in chat, which is all very good. Good, right, Jake's there. We'll do a poll as well. Let's do the poll. Here's the poll. Poll would like to know, how's your day going today? Sun shining, in Oxford at least. We've got a maths puzzle on the screen. What could be better, right? I think we're broadcasting live in the middle of people's mocks and stuff, or even exams and stuff. So it's astonishing to me that people have voted for, the higher star rankings. But maybe that's just because people are having such a bad day that they're off the end of not joining in live. Sometimes I overthink these polls, right? It's statistics, isn't it? Numbers. Jake is studying maths. I'm saying that out loud because you can't see behind the poll, but Jake's just answered a question for what they're studying. Good, right, okay. So the key thing about this puzzle on the screen, by the way, is that every label is wrong. Not just two of them are the wrong way round. Everything is the wrong way round. Everything's wrong. So it's not just the case that these two are the wrong way round. It's actually the case that all three labels are wrong. That's key to the puzzle. If that's not true, it doesn't really work. There's another thing going on, which is that this one says mix. I'm going to circle that and then get rid of it. This one says mix, and mix means there's some lemons and some limes in that box. That's less important, but still there. Right, people are voting on how their day was, and their day has been pretty good so far. I'm keeping the poll up slightly to hide chat where people are answering the question, but let's have a look at that now. If you are watching the replay and you don't want to see the answer yet, look away now or pause the video. I think you can actually pause the live. I'll stop talking. Stop talking. There we go. Cool. Right, people are answering in chat. Let's have a read this. It was honestly the wrong link. Okay, links to literally the live stream, if you're wondering, which is a troll that people have done on me before. People in chat want to take the, I think Johnny and Miles want to take one out of the mixed box, check the right crate and find out whether this one is lemons or limes. Let's work that through. So that the strategy here is, we don't know which way round the labels are supposed to be. We don't know what's in these crates. But I guess the strategy is we look at what's in this crate, and when it turns out to be a lemon, we now know something about this crate. We know that this crate isn't a mix because the label's wrong, and it's not all limes because it contains a lemon. So this crate must be the one that's all lemons. So this label's supposed to go over here with this lemon. It's kind of interesting that we know that everything else in the box is a lemon, even though we've only taken one fruit. We can do better than that. Because we can now sort out the rest of the labels. Chat with me? I'm not leaving anyone behind. We can now sort out the rest of the labels because, or maybe let's get chat to explain it. Has chat actually got this? You know the one with the other fruit in it has to be the other one. I sort of know what you mean, I think. If there's a lemon, the box is labelled lemons, it's limes, and the one labelled limes is mixed, vice versa. Johnny's given me the resolution of which way around it is. Hi Charlie. I think the best way I found of thinking about it is this label's got to go somewhere. If I just slap it on this crate, that's no good because this label's also wrong. So probably I should slap it on this crate and put this label on that crate. And of course do something different. If it turned out to be a lime, then switch them in a slightly different way. Yeah, when there's all limes, it's got to be over here. Can't be the middle one because that's where the label was. It can't be the right one because that's got a lemon in it. Let's check. I think I said, yeah, I did set that. There we go, brilliant. So this puzzle, if we're analysing it, has a couple of elements to it, which I mentioned. Oh yeah, right. There's a couple of things going on. One is I really like this kind of chain of deduction, that as soon as you've seen one thing, you can infer stuff about other ones. Oh yes, here's an XYZ thing. Yeah, Michael, I agree. The limes one has to be over here. There we go. Labels sorted. There's this kind of chain of deduction. It reminds me a little bit of the way sometimes towards the end of a Sudoku puzzle, you've got you're doing a Sudoku. You've got like two possibilities for like which way round a couple of numbers could be, and then if you knew that, then somewhere else you could put in a couple of numbers, and you end up with this kind of domino chain where you write in some numbers and they write some other numbers, and that implies something else, and then you do something else. Oh, that means that has to be a 6, 9, 8. You can sometimes set up these quite long domino chains of reasoning. This is quite a small chain that we saw a lemon and then deduced two things. But you know, you've got to start small with your domino runs. Yeah, you can think about it shuffling to the right or left. This is an alternative way of thinking about it, I think. Either if I sort of reset the puzzle, if you've just joined us, hi, this is the puzzle. All of these labels are wrong in a mysterious way. There are only actually two ways that it could possibly be. Maybe this is lemons. Oh, that's horrible. Let's go. There we go. Maybe this is lemons. No, not lemons because it says lemons. Maybe this is limes, or maybe this is mixed. Maybe this is lemons, or maybe it's mixed, but these two can't both be mixed. So there's only really two possibilities here. If this is limes and mixed, then this will be the lemons one, and if this is mixed and lemons, then this will be limes. There are these kind of two possibilities. You're either in the case above the line or the case below the line. These are the kind of two shuffles. Someone in chat's called these shuffling. And the best way to tell the difference, I think maybe the only way to tell the difference, is to sample from this box and find out if we're in the top case where we see a lemon or the bottom case where we see a lime. This shuffling thing is very interesting to me. Shuffling and fermentation. Brilliant. First, this mixed and limes. Shuffling is very interesting to me. The mix thing is a little bit of a distraction, I think. There's sort of nothing too wrong with the puzzle if you replace the mix of lemons and limes on that label with oranges or something. It means the puzzle doesn't have a unique solution because you can look in any box now, they're kind of all the same. If it said all oranges on that one, then it's kind of like a third citrus fruit, so they're kind of all the same. That gives the puzzle a kind of nice pleasing symmetry that you can look anywhere and then make some deductions. All that changes in this logic down here is you write the word oranges instead of the word mixed. So it's kind of a different version of the puzzle. Choose a crate, take a random fruit from it. Oh, this is your starting point of your labelling process. Examine the fruit, size and distinct features. Right, good, yes. That's a lovely description, thank you. Yeah, hi. Can we control the fake names a little bit, please? Can we reel it back a little bit, thanks. Okay, so there's this kind of nice symmetry. People in chat using X, Y, Z or ABC. Lemons, limes, oranges, also acceptable. Okay. I saw this puzzle, maybe not the first time, but one of the times I've seen this puzzle was in a movie. It's a thriller movie where some mathematicians are stuck in a room and all of the walls are closing in and they have to solve puzzles. And this is one of the puzzles that they have to solve in the movie. The movie has mixed reviews. Thanks, Jack. Good. Right. Okay. Right. The movie is called Fermat's Room. I don't know why I didn't tell you the name of the movie. It's not a secret. The movie is rated 15. Is that appropriate to mention on the live stream? The live stream doesn't have an age range on it, right? Who knows? Something I want to set you to maybe think about, back of your mind, is a different version of the puzzle with the same setup, but where the boxes are labelled slightly differently. Lemons, limes, oranges, and then a fourth box that says pears. And the question here is, how many boxes do you need to look in? All labels wrong. So again, we've got some incompetent labelling going on, where we've got these 4 boxes and they're all labelled incorrectly. In fact, that's information that they're all wrong. It's sort of information in a way. Got to look in some boxes. 3 because after okay, so choice is either 2 or 3. 3 because. Or is it actually written by AI? Sorry, 3 because after 3 you know what's going on. That's plausible. There's also a case for 2 with a question mark. 2 with a question mark is a question, which means we ask it back again. Michael's got a plan for only 2 boxes. I suppose maybe if you've got a plan, you might like to think about how your plan works and make sure it really does work, whatever happens on those first 2 boxes. And you might like to think about what if n boxes instead. I'd like you to maybe have that at the back of your head. This version of the puzzle is not in the movie that I saw. This is just sort of harder version. Something I like is making up harder versions. If you've got a strategy, there might be a strategy that's better. Unless you can prove that there's no strategy. If you look in none of the boxes, then you're in trouble because you're not going to be able to fix the labels. If you look in just one box, I think it's maybe obvious that if you look in just one box, that's not okay. So maybe it's 2 or 3. And I've got n-1 in chat, which equates to 3 in this case and 2 in the previous case. Maybe special cases for 3, who knows. Okay, good. I'm going to adjust the curtain because the light is extraordinarily bright and it's in my face. There we go. Pop, wait for the camera to correct for contrast. Right, okay. In general, these things where everything's wrong are called derangements. It's a good word. Because it's like arrangements, and when things are arranged. Derangement is when they're all mixed up. Also, it sounds a bit like the word deranged, which means crazy. Maybe 2 or n-2. Not sure about 2. 2, I can sort of see how 2 feels like you look in a couple of boxes, you see what's happening. It's possible that you can still be confused after. I'll give you a clue, I suppose. It's not the case that you can just pick 2 random boxes, look at what's in them, and be done. that sometimes doesn't work. So there's a little bit of subtlety here. Let's go, which ones? Or let's make that more specific. What's your plan? Like, you can't really tell me which ones, but yeah. Your plan could be based on what you see as you open boxes. Okay, maybe have that in your back of your mind. If you think it's 2, try and prove it's 2. If you think it's n-2, try and prove it's n-2. If you think it's better than that or worse than that, or 1 box, 3 boxes, oh my goodness. If you're looking at all 4 boxes, you're good. Okay. Good. Okay. I'd like to talk about something else. My plan for today, I think, is to come back to this at the end, having done something traditional, something less traditional, and something weird. So I've got a kind of traditional lesson plan for a bit, and then I've got an untraditional lesson plan, and then I've got, oh gosh, just some slightly experimental thing, which we'll try and do in that order. Live stream is running today. We're all going. Here we go. Text in chat. Oh gosh, right, okay. Detailed plan for 2 boxes. Cool. I kind of want to teach you the Inclusion-Exclusion Principle. I don't think I've talked about it on the stream before. Sorry if I have, if you've already heard about Inclusion-Exclusion, but I want to have a go at talking about it because it turns up in several different places. It is just kind of good in its own right, I suppose. The place it turns up in is when you're trying to count things, counting, but allowing for overcounting. Whoops. That's kind of the tagline. Prove it. Yeah, please prove it. Your proof is probably not just that your strategy works, but also that other people's strategies aren't better than yours, which is pretty hard to prove in general. That's why we're setting it and we're coming back to it in an hour. Okay. So, for example, a question where you might want to do some counting is, maybe this is too basic, but how many numbers under 100 are multiples of 3 or of 7? Multiples of 3 or 7. So, one way to do this is to sort of list the numbers up to 1 up to 100. And then start crossing them out if they're multiples of, or try circling them if they're multiples of 7, or multiples of 3, right? So I want these ones as well. What am I doing? I'm writing up numbers. I'm not really sure I like this plan because 100 is quite large. It's been a long day. I'm already getting a bit bored about working this out. And it's this sort of problem, right? That you end up circling. Gosh, what am I doing? Yeah, so double counting is when you count something twice by mistake. So there's this sort of problem that I can run into. If I just take how many numbers are multiples of 3 and think about that separately from how many are multiples of 7, then I'm in danger of double counting the ones that are in both. So it's a suggestion in chat. 3 calculations and 2 answers. So that's, you see, you've got 3 calculations but 2 answers because 2 of them are the same. That's an example of double counting. Yeah, cool. So Johnny's got a plan here, which I like, and other people have put their numbers in chat as well, which is to think about like this Venn diagram, where you have like your multiples of 3. You have like your multiples of 7. And you can put numbers in here, so like 1 and 2 are not really relevant, they're not in either of these boxes, but 3 is over here, 7's over here, there's the extra like 6 and 9 and 14. But then 21 is in the middle. 21 is in both. There's this strategy to allow for the double counting, where you count everything in the left circle, you count everything in the right circle, and then you do some subtraction. What do you subtract? You subtract the number of things in the middle. You have to work that out as well. So here, the number of things in the left circle has, I think, 33 things. They are 3, 6, 9, all the way up to 99. Oops. The right circle, ... There's loads more things here. The right circle has, oh gosh, I think 14 things. Is it 14 things? 7, 14, 21. How good's my 7 times table? Not amazing. 91, 98? Oh gosh, yeah, 98's a multiple of 7. Why did I pick 7? 99's over here. So 14 things on the right hand side, but there's a few things in the middle. What are they? They are multiples of 21. Because things that are multiples of 3 and multiples of 7 are multiples of 21. There's a tiny bit of number theory hiding in the middle there. Say that if things are multiples of 3 and multiples of 7, then they're multiples of 21. So how many of those are there? I think just 4. 42, 63, 84. Yeah, just 4 of them. So a way to count this would be 33 plus 14. That's kind of an innocent, naive first guess. So I'll take the left circle and just add on the right circle. That's what I would do if there was no overlap. But then to allow for the double counting, I'll subtract the things that are in both. I counted them twice, so I subtract that many. So that I've only counted them once at the end of the day. There are 4 things in the middle circle. Did I get that right? Yes, I did. Good. The middle's got 4 things. Yeah. Oh, and there's loads of floor function stuff going on in chat. People are generalizing. Ooh. Floor of, yeah. Yeah, we're being very careful with our ABs. Yeah, being very careful. 21 is a multiple of 3 and 7. Yep, good. That's the problem. Yep, okay, good. We're going to generalize this a little bit, which involves bringing in lots of letters and a little bit of set theory, I think. But at its heart, that's what I want to write down next. Left circle plus right circle, take away the bit in the middle. That's loads of words. Having symbols is good for this. What people normally do is they write sort of A for this set. So this is maybe the set A. And maybe we've got a set B. And there's this notation that people use for the bit in the middle and the totality of both of them considered together. It's written like this: A intersect B, that's pronounced A intersect B. Is the middle bit. Or sometimes people say A and B. That can be a little bit confusing, but yeah, the intersection of A and B is like a long phrase, but we're looking for a short phrase, right? This bit. And something else that we're interested in is A union B, which is everything that's in either set, counted once. This is sort of A or B. But sometimes that gets a little bit confusing. Multiples of 3 or multiples of 7. Yeah. Okay. In chat, people are using a capital U for this one and a capital, looks like capital N for that one. Fair enough. I always think a lowercase n would be more convincing. Oh, floor. Welcome to floor function. Quick detour to floor. Actually, somebody in chat who was typing floor functions before, challenge, please explain floor function in a chat comment. Let's do that. Good. A or B, A intersect B. The result is this counting thing that we were doing before, that the number of things, which is like the size, you put these kind of vertical bars on either side of it, the number of things in A union B, counting everything together, counting once, what you're supposed to do is take all the things in A, count them, take all the things in B, count them, and then subtract, because you double counted, subtract the things that are in the intersection. Okay. So looks really complicated, but to spell it out, on the left it says to count everything once, you can just count the stuff in A, count the stuff in B, but subtract the stuff in the intersection, A and B. Yeah, that's pretty good. Truncate all round down. Floor, yeah, cool, okay. Thank you, floor guy. It's sometimes written, and I like this quite a lot, it's sometimes written like this, where the little bars are showing you that you're taking the thing below, rounding down. Sometimes people write largest whole number less than x or equal to x. That's the floor function. There is also the concept of a ceiling function. Written like this. Oh, without the little, yeah, didn't quite get that right. There we go. With the bars at the top, the little horizontal bits at the top, where you round up instead of down. It takes it to the ceiling rather than taking it to the floor. Charles has identified themselves as floor guy, or maybe they're doing a sort of Billie Eilish quote. Who can say? There's some sort of, maybe they're claiming it. Yeah, okay. What if there's three things? Can we get A or B or C? We've got three criteria. Good question. You got to keep track of all the double counting. It's not impossible. We're going to do that. Now, if people are happy with this, bit of subtracting. We're running out of names for functions. Ceiling function and floor function was great. Those are brilliant. Window functions, you've got to round the number sideways. Now, that doesn't really make any sense, does it? Because we're already using up and down for the number line, and the number line is 1D, so there's no such thing as sideways. So in order to have a window function, we would need some sort of 2D number system, I think. So not the real numbers along the number line, because that's ceiling and floor. So we'll have to wait until somebody invents that sort of sideways dimension before we can have any window functions. Right. Oh gosh. Good stuff. Nervous chuckle as people suggest new functions. Right, let's do the 3 version because there was a request in chat. The counting is awful. It is this thing in chat, by the way. Well done. If you've got A or B or C and you want people to string these things together, so people talk about the totality here, counting everything inside there once, A or B or C for everything that's inside these circles. What you can do is you can start with, and I'm going to put a wait for it here because this is going to be quite long. We're going to try counting them and try fixing our mistake. Yeah, cool, very good. So my first guess is to just add together the size of the things, which has problems. I'm sure you can see the problem with just adding together the size of A, the size of B, and the size of C. It does a lot of over counting, right? Actually worse than double counting. That counts these bits once. It counts this bit twice. The stuff right in the middle, we've counted it, I think 3 times. Because it's in A, and it's in B, and it's in C. So we've done a bit of triple counting as well. We should fix that. So this is not yet done. It says wait for it. We're not yet done. The systematic way to do this is to fix. We start with just the sets, and then fix working our way inwards. Gosh, right, okay, I can do this. So I'm supposed to subtract A intersect B. Subtract A intersect C. I'm trying to pick out these bits where they overlap. Subtract B intersect C, and then, oh my goodness, have I fixed it? So what I've tried to do is subtract off the intersections, like we were doing before, right? We had those, I had this idea at the top of the screen there that you subtract off the intersections. Let's see, how many times does this stuff get counted now? So out here, the stuff here got counted once because it was in A, it got counted once because it was in C, then it gets subtracted because it's in A and C over here. It's not in these ones. A and B, it's outside B, so it's not involved in those. So that's now being counted 0 times. One time. 1, 2, 1 plus 1 is 2, take away 1 is 1, quick maths. Yep, okay. Okay, the hard question now is, are we done or do we need to worry about the very middle? So chat, with the current expression on the board, how many times have I counted the stuff that's right in the middle? If it's 1, we're done. This is now inclusion and exclusion for 3 things. How many times has it been counted? Or possibly Pascal's triangle. I don't even wait for chat to do this, I think. There's a counting argument, right? We counted it and then we subtracted it a few times. We got votes for 3 times, we got votes for 0 times. So it gets counted. Let's see. Let's give some thumbs ups. Okay, I'm getting up some more. He has more numbers. Sorry, Jake. Jake has now got to watch everybody shouting numbers in chat. Yeah, consensus at the moment seems to be 1 or 2, or mostly 0, with some votes for 3 and some votes for 0. So the stuff right in the middle, let's count it. Yeah, loads of 3s, right, good. Okay, it gets counted once because it's inside A, it's inside this circle, once because it's inside B, once because it's inside C. So at this point we've counted it 3 times, it was pretty bad. But then we do some subtraction. This stuff in here, right in the middle, is inside A intersects B. That overlap between A and B, oh no, that makes it look like B, anyway. That overlap between A and B counts all of this stuff and it's been subtracted. So it's been subtracted. So anything that was in here got counted 1, 2, 3 times, and then after this we subtract 3 times, so it ends up not being counted at all. This is very complicated, isn't it? What's a way to be more convincing, right? Well, some votes for -3, which would be too much subtraction. -3, gosh, okay. I think it is 0. I think it's been counted 3 times by being included in each of these things, and then I think it's been subtracted 3 times for each of these things. So I think it's now not being counted at all. So I can fix that. Fix 3 times, so you add fixed 3 times, subtracted 3 times. Good use of the word thrice. So add in A intersect B intersect C. Okay, add 1 in, and then after that, phew, finally, we're now good. This has now been counted once, but kind of like 3 take away 3 plus 1. Feels a lot like Pascal's triangle. Yeah, just add in an A and B and C. Well, I can now delete the weight for it because I'm now done. Ugh. This is kind of hideous, right? It gets better the more you look at it, but still, it gives us a way to work out the size of everything inside A or B or C, provided we can work out all of the things on the right hand side, and there are lots of things on the right hand side. Let's think about, maybe as an experiment, we could try multiples of 3 or 5 or 7 below 100 or equal to 100. I've got to decide now because 100 is a multiple of 5. A mathematician might have written that as less than or equal to. Oh yeah, okay, it gets better, right? Keep looking at it and it gets better the more you look at it. So, gosh. The maths for this looks a bit like this, I suppose. There are 20 different multiples of 5. I should really put bounds on this, right? Am I counting 0 or not? Am I counting negative numbers? This is awful. Let's put 1 less than n. There we go. That'll do. Between 1 and 100 inclusive. Is that clear? Oh no. Oh, it's more like alternating signs. Yeah, okay. It gets better the more you look at it. I'm going to leave it on the screen while I do this little calculation at the bottom. I'm going to keep it on the screen. Oh my goodness! So the size of A and B would be things that are multiples of 15, because they've got to be multiples of 3 and 5. Multiples of 15 go up to about 90 before you've got too many of them. Size of A and C is multiples of 3 and 7, which is 21. We did that one before. I can't remember it. Oh, it was 4. Size of B and C would be things that are multiples of 35. There's only 2 of those. And things that are multiples of A and B and C would be, oh my goodness, I've gone off the screen. Things that are in A and B and C would be multiples of 15 times 7 is 105, and none of them. 105 is too big. Multiples of 5 and 7, 2, yes, thank you. Is it 55? Let's work it out. So inclusion-exclusion on the board says, first guess is to add together these first numbers. That's just counting multiples of 3, multiples of 5, multiples of 7, as if there's never any overlap. Disastrous idea. You're supposed to subtract to allow for the overlaps, but the overlaps of the overlaps have now been counted no times, so add those back again. Although actually in this particular example, there are none of them. So gosh, what does that make? Why did I do this 67? take away 12. Is it 55? Hooray! I've agreed with Michael in chat. Okay, horrible calculation. Possibly not an interesting answer. Not that interesting, I suppose. Heavily reliant on edits or. I regret the example, right? Because there's no zero. There's a 0 on the end. I should have made it 200. Should plan my examples in advance, right? Should plan them in advance. Good. Okay. Yep, chat's there as well. I'm going to let chat come through a little bit. Okay, good. Okay, there's a little bit of lag for chat, but we're there. Okay. Who was it who said something very interesting? Yeah. That's a little bit like the... Gosh, yeah, there's a thing about roots of polynomials. Let's not do it now. There's a sort of alternating Charles and I think Miles to give credit. Sorry, just going off the bottom of the screen there. I think Charles and Miles was one of the, it goes sort of plus signs then minus signs. Then we had to put a plus sign back in. And just like before with the crates, where people want to go from. It's like before with the crates, where people want to go from 3 crates to n crates. There's a question of what's coming next. Let's go down a little bit. There's a question for the Venn diagram. Yeah, okay, let's have a go at the Venn diagram. So I would draw it like this to start off with. Maybe I regret that because there's nothing in the middle. So maybe I would draw the Venn diagram like this. Because there's nothing that's in all 3. Like a kind of donut-shaped Venn diagram. Why not? Who's going to stop me? Nobody's going to stop me. I can now put in numbers like 3, 6, 9, 12. I'm panicking a little bit. No, I'm fine. 15 goes in this box. 18 goes over here. 21 goes over here. These are multiples of 7. A, B, C. Oh my goodness. There are numbers over here like 35 and 70. There are numbers around here as well. Oh gosh, I'm not going to do it. I'm not going to fill it in. The thing maybe about trying to draw Venn diagrams with more intersections. The next one I want to draw, right, is the one with 4. But unfortunately, if you just draw this, it's kind of unsatisfying. Can you see why? I mean, it's nice and symmetric, but it feels a lot like, yeah. I sort of don't love this Venn diagram, right? For like A, B, C, D. If I've got 4 things, doesn't really include all of them. 3 dimensions needed. Alert! Call the extra dimensions, people. Can you do something with spheres? Can you actually? Oh gosh, I haven't really thought about this. Wait, are you trying to do something with spherical Venn diagrams in 3D? This is one of those chat messages where I can't tell if the person who typed it has an amazing idea that I'm not keeping up with. Ellipses. Yeah, you can do something with ellipses, I think. You can do some stuff with nice shapes. Anyway, this is what point maybe that with 4, the Venn diagram starts to be less helpful. I'm trying to imagine this 4 spheres thing now. Maybe I should not imagine it and carry on presenting the live stream. Yeah, it doesn't include A and C, but not B and D. Or A and C, but neither B nor D. I kind of want a bit where A and C overlap, but without B and D being involved at all, without them necessarily being involved. Like how in the 3 diagram in general here, I've got this lovely region over here where A and B are involved, but C is not involved. I can choose. Maybe C is involved. Maybe C is involved. Maybe C is not involved. I've got both options here. Whereas here, if I'm looking at A and C at the same time, I've got these 3 bits, but I don't have an option for A, C, not B, not D. That's just not in this picture. You can do something. Miles is secretly Pascal's triangle, but I'm trying not to make everything about Pascal's triangle. After last season, when I made everything about Pascal's triangle, I think people got a bit fed up with me making everything about Pascal's triangle. This is as much Pascal's triangle as you're going to get. That looks like Pascal's triangle. It's the counting argument. Could you use a different shape to make it work? Yeah. Let's try and invent this. Should we invent it? We could look it up. Other people have done this before. But I think there might be more fun in trying to invent it. my first idea is to use, so I saw ellipses, but using wobbly shapes. I saw ellipses in chat, but maybe I want things that are a bit wobbly. And then the idea would be to draw something that intersects. So this next one has got to go through, it's got to go through the intersection. It's also got to go through the outside bit, so they get all of the possible combinations. That looks nice. And then I've got to put a fourth one in, and I'm not really sure where to put it. So that's 3. How do you do 4? And then my next thought of how to do Venn diagrams is that, oh, forget this, do something nice and symmetric. Just take an ellipse, rotate it a little bit, rotate it another bit, rotate it a bit more, see if that's worked. Has that worked? No, not really. Okay, that didn't work either. Nice and symmetric. Right, okay. Next idea is forget symmetry entirely. Take something like the number line. Circle the multiples of the first 4 primes. So like the thing we're doing here with the primes and the multiples does actually work. So if you're allowed weird shapes, then I'll do something like this, which circles the multiples of 3. That's one of my Venn diagram shapes. Goes on forever. Maybe I'll stop at some point. I'll stop at a trillion or something. My next shape is the multiples of 2. Is this working? This feels quite convincing. I don't think I've quite finished yet. And then my next shape is going to be, I should be doing these in different colours. My next shape is going to be multiples of 5. And I'm going to be really careful to just circle the multiples of 5 and not the other numbers. My plan here is that the Venn diagram thing will overlap in just the right places. Okay, cool. I'll cut that off after like the product of the first 4 prime numbers or something. And then the intersections are all there on the relevant numbers. Is 8 not a multiple of 2? Did I miss 8? God. Oh. You heard it here first. Oxford confirms 8 is no longer an even number. Sorry, 8. Sorry, fans of 8 in chat as well. Right, good. That's my next attempt at trying to do overlapping Venn diagrams. You can probably find nicer things on the web, and I'll probably link to some in the further reading. Right, but what are we supposed to do? What are we supposed to do? We're supposed to do some sort of counting argument. The counting argument's really good. It works like this. The answer is just you put plus signs and then you put minus signs. I'm going to try and defend this. So this has counted everything that just lives in like each set. Normally the intersections are a big problem. The intersections have been counted, well, first off, let's think about A and B. That's been counted twice. We should subtract because A and B has been counted twice. We should subtract all of the intersections, and oh gosh, there are a lot of them now. If you're playing along at home, you might be better at the alphabet than me. I seem to be having a lot of trouble with the alphabet. And you might know how many things there are in that row, especially if you like Pascal's triangle. Right now, the things where 3 sets intersect, for example, A and B and C. A and B and C is kind of like how we discussed before. It's been counted 3 times, and then it's been subtracted 3 times, so it needs to be counted. The crucial bit to sort of understanding why the structure's like this is that each line I'm writing down is kind of the same as the previous argument we were running. Fans of Pascal's triangle, there are also quite a lot of these. Yeah. There was a dangerous bit about earlier this year where it really felt like the entire live stream was going to be Pascal's triangle themed forever, which we did break out of eventually. What on earth am I doing? There we go. Right, good. Last one. Probably there's a pattern you can see now coming together. We counted this middle intersection a confusing number of times. The bit that is A and B and C and D. It's been counted 4 times, and then it's been subtracted 6 times, and then it's been counted 4 times. So it's been counted altogether, twice, because 4 take away 6 plus 4 is 2. So we subtract 1. subtracted at the end. So there's a little bit of thinking there to think, green's being subtracted. But in general, this is the pattern that you always end up with. But the uni on the left here is the sum first of the sets, and then subtraction for the two set intersections, then add the three steps, and then keep going, alternating plus and minus signs. Yeah, okay. 1, 4, 6, 4, 1. Good, right, okay. The sum of all of those things is a power of 2, which is something we said back in one of the Pascal's triangle episodes. So that's nice. Okay, I think I'm not going to do an example with this one. I'm going to leave that there. I want to do something with the inclusion-exclusion, which is counting derangements. These ways of mixing up everything, getting everything wrong. There's a way to use that to just sort of count how many there are. And it points towards a good way of just counting complicated things. So even if you've seen this before, I'm going to do it now, I think. I think we talked about derangements before on the stream. I want to do the double bit as well because it's a fun coda thing on the end. We'll do that when we get there. Have definitely said some of that before on the stream. Okay. So let's think back to those crates with the labels. Every label is wrong. Another way to say that is it's not the case that the first label is right, or the second label, or the third, or the fourth, or any of them. That's not the case that any of them are right. If we could count the ones where some of the labels are right, we could count how many ways there are where all of the labels are wrong by doing an easy bit of subtraction. This is a little bit like probability, where you think about sometimes the probability that something happens, you get there by thinking about the probability that it doesn't happen. Like in that kind of birthday paradox thing with 23 people. Say in chat, if that doesn't mean anything, say in chat, because I'd love to do that but I feel like the 23 people birthday problem has happened before. Who knows? So the key to using inclusion-exclusion is always to set up your sets very carefully. I'm going to use some sets A like this. I think I'll use letters. I'm sort of not in the mood to do subscripts. Maybe I am. Yeah, maybe I am. Can I have this if I have A1 and A2 and A3? It's just easier than running A, B, C, D because the alphabet's really tricky. If you've just got here, we're counting the number of ways to get everything wrong. For example, if you've got 3 crates with all of the labels wrong, how many ways are there for all 3 labels to be wrong? Surprisingly, it's only 2. So I'm going to have some sets. We're going to use inclusion-exclusion, and I've got some sets ready. In particular, I'm going to be interested in the case with 4, where we think about how many ways there are to have 4 boxes with all the labels wrong, but there's nothing really stopping us from going further because we've got this inclusion thing. Oh, don't know. People don't know the birthday paradox. After this, 10 minutes and we'll do birthday paradox. That's a different thing. Good, okay. So I'm going to let A1 be the set where it's going to be the set of all, what are we going to call these? Label arrangements, where the first label is correct. So there's lots of ways to do this, where the first label is correct. Maybe the others are right as well, maybe not, but hey, the sticker person putting the labels on the boxes, not total failure, they got the first one right at least. That's an achievement, I suppose. This one's going to be the one where the second label is correct. This set's going to be the one where the third label is correct, and this one's going to be the one where the fourth label is correct. And what I really want is something like n factorial, the total number of ways. 4 factorial? Whatever, yeah, 4 factorial. The total number of ways of sticking labels on the boxes. There are 24 things they can do when they've got 4 crates. 4 factorial is how many ways to just shuffle shuffle the deck of cards, shuffle the labels together. 4 factorial is how many ways they could do it, and if they're getting everything wrong, then it is not the case that they've got the first label right, or the second label right, or the third label right, or the fourth label right. So somewhere instead, so one of these has gone wrong, or at least one of them has gone wrong. Okay, so label is great. Well done, sticker person. I'm not sure why I'm writing this out. There we go, good. Okay, so 24 things that they could do. Sometimes they get the first sticker right. Sometimes they get the second sticker right. Crucially, sometimes they get both of them right. Let's build it. Let's work into this. So, for example, the sort of set of ways where they get the first label right is, okay, we've got label 1 is on box 1. That is correct. Well done. And then we don't know what's going on the other 3 boxes. Could be anything. Could be anything at all. All we've said in this case is, well, they got label 1 right. You started the day well, applied the correct label, and then who knows what happened in here. So the size of this is 3 factorial because there are 3 other labels for them to shuffle around. If their goal is just to get the first one right, then there's still 3 stickers left for them to apply, and oh my goodness, they could get that really wrong or really right, who knows. Okay, so that's kind of the size of how big is that set A1. Similarly, this is the size of A2 is also 3 factorial, and the size of A3 is 3 factorial, and the size of A4 is 3 factorial. Those are all 6. Those are all 6, and this thing's 24. So if you do some double counting, then you might conclude that it's impossible for them to get them all wrong because there are 24 ways for them to label the boxes. In 6 of them they get the first label right, in 6 of them they get the second label right, in 6 of them they get the third label right, and in 6 of them they get the fourth label right. But that doesn't mean it's zero ways for them to be completely wrong overall because of the overlap. The overlap between the times when they get more than one label right. So it starts off with 24 ways to put the labels on. If we remove the ones where they get one label right, we should think carefully that they might have got 2 labels right. I suppose on average they get 1 label right by shuffling the labels at random, let's say. But sometimes they get more than 1 and sometimes less than 1. Okay. There's the calculation in chat. Look at that calculation. Good stuff. Gosh, my maths is slow today. There's a 1 in there, which makes me feel like it should be an odd number. I feel like I got an odd number before. Anyway, yeah, okay. Is it 9? We'll find out in a second. To allow for the cases where they got 2 of the stickers right, let's have a think about that. Maybe they put sticker 1 correctly and sticker 2 correctly. Brilliant stuff. I don't know what they did with stickers 3 and 4, but they got off to a roaring start. They got 2 of these right. The size of this set is 2 factorial. 2 things that might have happened on those last 2 crates. I guess either they were right or they were wrong. Similarly, the other ones like this have size 2 factorial, and similarly, the ones where we have an intersection of 3 things have size 1 factorial. There's only one way for them to get 3 labels correct. Which actually means that once they've got 3 labels correct, they get all of the labels correct. But the nice thing about this argument is we don't really need to know that. We don't really need to think that. We've got a method for counting intersections. How many ways are there for them to get all 4 labels right? Oh, just 1. Just 1. Put the labels on the boxes in the right order. That's all we asked for. Plus 1 is 9. Okay, good. Okay, so the calculation is a bit horrible, but using the formula from before is 4 factorial minus 3 factorial times 4 plus, oh gosh, 2 factorial times 6, because there were 6 things in that row, all of the intersections of 2 things, 6 of them, minus 1 factorial times 4 plus Oh gosh, just that 1 on the end, right? 0 factorial times 1. I want to put a 0 factorial in there, it just feels right. I guess this 1 here is secretly a 0 factorial. I put a 3 factorial here, but that's completely wrong, it's 1 factorial. Oops. Oops. Sorry everyone. Sorry if you're shouting me in chat. Good, okay. I think this adds up to 9. But my maths is not very strong today. 12 divided by 4 is 8, plus 1 is 9. Yeah, cool. Should we try and list them? Should we try and do it? There's 9 ways for them to get all of the labels wrong. It's sort of almost worth it. All wrong just by listing all ways on paper. Oh, you've gone for it. Sorry, 4 times 3 is 12. You've gone for it. There's a claim in chat, I think, that it's actually 12. They've just listed all of them. 24 is not that big, right? So I guess your plan could be systematically list all 24 of them and then cross out any row where they got one of the stickers right. How many rows are left? I'd like to show you a different way of doing this puzzle, doing this counting. Because maybe this is not your cup of tea. I think there's a different way we can think about this. To think about the swaps. Whether you like this or not depends an awful lot on how you feel about swaps of things. So I'm just going to try and get there. 9. Okay, so thing in chat, I guess this won't really fit in chat, but if you want a challenge, there are apparently, according to some complicated theory, there are 9 different ways to get the items A, B, C, D all wrong. For example, B, C, D, A is a way to get all of them wrong, all of them in the wrong place. Apparently there are like 9 of these in a sort of list, including some, I guess, some weird ones. A different way to think about this is to ask the question, where does label 1 go? This is a bit like when we were solving the puzzle, we opened one of the crates, we looked at a fruit, and we asked what's going on. There's sort of several possibilities. Well, I suppose when you look in box 1, you'll see in there an item of type 2, or type something else. You'll see something else, because that label's wrong. So what we did in the lemons and limes puzzle is we kind of followed that. We followed that trail. Ooh, someone said R factorial 4CR. Yeah, there's something going on there with some minus signs in there as well. Oh, here's a trick, by the way. Minus 1 to the n is equal to, it's like plus 1. If n is even, minus 1 is if n is odd. Sometimes that's helpful. I don't know. Maybe somebody in chat needed to see that. I don't know who. Minus 1 to the n. It's a good trick. See also cos of n times pi or something, radians or something. Who knows? Sometimes these tricks are helpful that you have some way to write down alternating plus and minus signs. Who knows? Right, I was going to tell you a different way of looking at the rearrangements, which is to open box 1, find out what's in there, go and look and see, oh, actually this contains something of type 5, and then use that as a kind of mission to go see, oh, it's over here, what's in box 3, go and look at what's in box 4, go and look at what's in box 6, go and look at what's in box 4, like that, and find out that, oh look, the boxes are all like linked up into these loops, that things have been shuffled, they've been permuted in these separate cycles of how things have been mixed around. There are kind of different cases here as well that you could imagine. You can imagine maybe label 1 is involved in a cycle of length 2, so just a swap, like this. You open box 1, you look at what's in there, you find it's something like this, and then you open that box and you find, oh, that's where the ones were. Those 2 labels have just been switched. Or maybe it's involved in a cycle of length 3 or a cycle of length 4 up to a cycle of length n. These are these separate possibilities. I'm not going to spell this all out because it's not super exciting, but this gives you a way to say that the number of derangements, let's call it dn, satisfies D0 is 1, and then dn is equal to, and this is a bit mad, but we're going to go with it, n minus 1 times dn minus 2 plus n minus 1 choose 2, what do I mean here? 2 factorial dn minus 3 plus n minus 1 choose 3 factorial dn minus 4 plus dot 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 and so on and so on and so on. dn. Yeah, good. Plus keep going until you get to, I guess, the last one in this sequence is going to be dn minus 1 dn minus, choose dn minus 1 plus dn minus 1 factorial d0 times n minus 1 factorial d0, which is a pretty mad sum. I'm not going to spell out where this comes from. 10 ways. Oh gosh, a challenge in chat. We've been challenged. Are 2 of those the same, or does one of them have something in the right place, or is this all wrong? It's like a little game. 4 of them start with 3, that's suspicious. 3, 1, 4, no, 3, 2, 4, 1 has got 2 in the correct place. Okay, did it. Where's this one? No. Puzzle. Good. I don't want to spell this out, but I will give you a hint that it says that the number of derangements, if you think about the cycles, is just nice. You get this choice about what you put in the cycle. So maybe it's in a cycle where you've got to choose what else is in that cycle. Those are all different possibilities. You know, you open the lemons box, maybe you see limes or pears, who knows. And then so maybe you build a longer cycle, which involves more choosing, because as you go through the cycle, you've got to choose more things, and the order matters. So these are really permutations rather than combinations. Anyway, you're choosing some stuff to be in the cycle, and then after you've chosen that, you're supposed to derange the remaining things. The number of remaining things depends on how big that cycle was that one was in, and then derange the remainder of the stuff. Yeah, okay. If there's 6 things, you can't have a cycle of 5. That is true. The term before last in this sequence is a bit weird. The term before last in this sequence of things that are being added together, this one here, is n minus 1 choose n minus 2, n minus 2 factorial d1. Gosh, that was hard to work out. This is the term before last. And weird fact, d1 is equal to 0. There are no ways to derange one item, which is the fact you're telling me, right? There are no ways to derange one item. That actually follows from something in here that, like, d1 is equal to 0 times d. Never mind, not important. Yeah, there are no ways to derange something. So d1 is equal to 0. It appears in the term before last. So if you're 6 items there, you're right. There are no cycles, no way to do a cycle of 5, because you wouldn't be able to derange the remaining one. It's a massive recursion involving all of these previous terms, which is pretty wild. So this method is a little bit more like, it reminds me a lot of these recursion questions that turn up on MAT in computer science questions. So we've got this kind of pure inclusion-exclusion thing, which is very pure maths. We've got this recursion thing, which feels a little bit more computer science to me. There's also an applied maths answer, which I want to show you. The applied maths answer to the number of things is that it's the integral, the number of derangements is the integral from 0 to infinity of e to the minus x, yes, that e, x to the minus 1 to the power of n dx with respect to x. So this is sort of mad that this is just the number of derangements. And I'm calling this applied maths because the person who I think discovered this, or the source I've got for this, is an applied mathematician who noticed, not just for this, but for a slightly more general problem, they noticed that this derangement problem has the same answer as an applied maths problem. They were interested in applied maths, and they realized that the answer to their applied math problem was the same as the answer to the derangement problem. Proving that two problems are the same is good, because then if you know the answer to one of them, you know the answer to the other problem. This is obviously mad, right? Because it's an integral. It's not obvious that this is a whole number. It's not obvious that this returns anything. There is a proof. The proof is incredibly good. We're getting there, I promise. A small hint of the proof. It's to do with thinking about cycles again. And if you know about integration by parts, then you know that for integrals like this, where there's a whole number inside the integral, sometimes a thing you can do is grab integration by parts and to use that to turn the integral into a related integral so you can use recursion on it. That's sort of the plan. There's some integration by parts. Yeah, haven't done this yet. Goodness. So there's a sort of aspirational combination here of integration with infinity in the limits, which is a bit weird, exponentials, which you might not have seen yet, doing that integral to get the number of derangements, not obvious at all. The proof involves integration by parts, so I'm not doing it now. Right, good, okay. But we're going to have a look at bits of it in a moment. I've got a lot coming. How are we doing? I really want to tell that story about the applied mathematician, but let's do the birthday problem. So the birthday problem is if you've got, if you have, is there a way to write dn without recursion? Yeah, here it is. It's that mad, right? No recursion, just do this integral. You've got 4 items? Yeah, okay, just go and integrate for me e to the minus x minus 1 to the power of 4 dx from 0 to infinity. Okay, alpha can do that, right? Let's have a go then. Integrate from 0 to infinity, x to the minus x, I want x minus 1, power of 4, please. It's 9, good, there we go. The answer is just 9, good. No recursion, just go and calculate that integral. 9, right, good. Okay, birthday problem, and then we're going back. I'm doing several side tangents at the same time. I think that's a great idea. If you don't like this, please fast forward. Okay, if you have n people in a room, what's the probability that there's a pair with the same birthday? And it's a sort of the problem is more fun if you make the following assumptions. 1, there are only 365 days in the year. That assumption's obviously false in the year. And 2, they're all equally likely for birthdays. That's also false, but never mind. So the way this works is that the clever thing to consider is 1 minus that probability to work out probability, instead to work out the probability that they're all different, which is kind of thematically related, which is why it's come up. It's thematically related that they're all different, they're all wrong. You have this first person who walks into the party, their birthday could be anything. Then the second person arrives, and we want them to have a different birthday if we're making them all different. That's pretty unlikely. The chance of that is 364 out of 365. What am I saying? That's really unlikely. That's really, it's really likely that they have a different birthday. Almost certainly. They've got a different birthday. The next person walks in, they've got to have a different birthday to both of those people who are already here, who have got different birthdays. So the probability of that is 365. 363 divided by 365. And the next person's got to arrive. There are now 3 birthdays in the room already. 3 people with birthdays in the room already. And the next person's looking at this kind of probability that they miss a birthday. These things are all pretty close to 1 and they're being multiplied together. The surprising thing is that overall this product gets really small really quickly. So that if you have 23 people in the room, so I need to write down 22 terms, so 360, let's go 23, let's go 40, why can't I subtract today? There we go. Is about 0.5. 50%. 50-50. Which is quite surprising. It's sort of 23 people. I regret that 2 already. I want that to be a 3. Subtraction, not my strongest suit today. So you've got this kind of coincidence going on. Well, not coincidence, but this kind of surprise, I suppose, that you'd think that maybe it would take like 100 people, 200 people before it's 50-50 that you've got a match. I can imagine 200 people with different birthdays, right? Not hard to imagine. There's loads of ways that could happen. I could also imagine 200 people where they share a birthday. It doesn't feel very likely. That's way more likely that there's a pair that share a birthday. Sometimes this is described as there are lots of pairs, which is not quite how this works because of inclusion and exclusion stuff about double counting. This product is kind of the relevant thing. This means that if you've got 23 people in a room, it's not 50-50 that they don't all have different birthdays. Some of them share a birthday. I've seen people do this on stage where they'll say, okay, let's try it. Let's find out if people have got the same birthday in this room. And usually when I've seen people try that, there's about 200 people in the room, so it's sort of not surprising. Maybe it's surprising that they can find it so fast after 23 people. We've got, by some sort of weird coincidence, 23 concurrent viewers. Let's not play the game right now. Other versions of this that I've seen. There's a related fact where you try and change the number 365. What's 23 got to do with 365? There's sort of some complicated relationship, right? That's roughly to do with square roots, I think. It's not a paradox, right? It's just a fact. It's a paradox because people think you might need more than 23 people to get a 50-50 chance. They think that if you pick 23 birthdays, probably all different. That's just wrong. I don't really like it when people say paradox just to mean I'm wrong about a thing, but hey, paradox is supposed to be more of an existential kind of disagreement between your belief and reality, and it's quite hard to convince people they had a belief about this. What's wrong with multiples of 100? Oh, right, yeah, the Gregorian calendar. Yeah, user safe, yeah, let's not bother. Okay, I want to talk about the integral. Oh, yeah, I want to talk about the integral. Let's look at the paper. This is a paper that I found because I wanted to know the answer to a question. It has an amazing history. I'm going to scroll through it very quickly. They're actually answering a more complicated question about deranging groups of objects. I've got an analogy for that in a mo. Their answer is fantastic. The general theorem here is this is something like the number of derangements on the left. There's a -1 to some horrible power out here. There's an integral, and then they've got all of these functions inside. Capital Pi here means multiply these together. They've got these different functions inside, which are called Laguerre polynomials. I think I'm pronouncing that right. I'm probably not pronouncing that right. Laguerre polynomials are, well, normally used in applied mathematics. They've got some relevance to the wave equation that I'm not going to explain. The story works like this. This is Joe Gillis, I think, was interested in this derangements problem as a teenager, worked out, for a more complicated version of the problem, worked out some recursion relations. Like we had a recursion relation there, thinking about cycles and thinking about relationships between different versions of the problem. So like we have this D thing with different subscripts for different versions of the problem. How many things are you deranging? Joe's doing a more complicated version of the problem. As a teenager, works out some more complicated recursion problems. I guess a bit like how some of you might be doing EPQs and you maybe work out some recursion relations for a slightly more complicated version of a problem. Didn't actually solve them, didn't get like a closed form solution, just had some recursion going on. And then many years later, as a professional mathematician, was working on Laguerre polynomials for applied mathematics, was working on their properties and discovered that they obeyed the same recurrence relations, the sort of related recursion relations. to the ones from the derangement problem, which, as far as anyone can tell, is just a coincidence. That the same guy who was interested in derangements as a teenager and found some recursion relations to them was later interested in Laguerre polynomials and found that they satisfied some recursion relations that were the same. And that meant that he could write this paper, which just says that the derangement problem has the same answer because they satisfy the same recursion relation. So skipping some of the maths in between, the recursion relation is really nice. It's got these things in here. The superscripts are related versions of a problem, and it says you sort of add together these related versions of the problem to get your answer. To show that the Pn and the Bn are identical. Bn's are the ones from multiplying, and the Pn's are from the derangements problem. To show they're identical, we're going to show they do the same recursion relation. So they're generated in the same way. So it's sort of amazing. The version that he's interested in, by the way, which I kind of want to describe because it's nice. The version he was interested in was where you derange things, but they have different sets that they belong to. I sometimes call this double derangements, which I quite like. The problem works like this. You've got some, let's say, Formula One teams, and they've each got some number of drivers in their team and some cars for those drivers, I guess. One car each. To make the sport more interesting, they agree that everyone's going to swap cars so that nobody is in the right car. That's not quite the derangement problem we did before, because it's not okay to swap, to just derange them like this, to swap the drivers over within the team, because then they're driving the same, car. The cars are identically built, they're the same colour. So that that's not what I mean by double derangement. What I want to see that the drivers are in the wrong coloured cars. So these green ones can't go here. So you might do something like this, where you keep the teams together, and say, okay, right now the Red Bull drivers are now driving Ferrari cars. The Ferrari drivers are now in Aston Martins and whatever. Okay, you might do that. That feels like the original derangement problem we did. But the reason the problem's interesting mathematically is that you don't have to. You could instead do something like this, where you mix up the drivers and the teams so that you've got everyone in a wrong coloured car, but it's a more interesting derangement. I call this double derangement because the drivers come in pairs, the cars come in pairs, they're kind of deranged doubly. There's kind of these other ways to derange them, where you separate out the teams. You can imagine this getting much more complicated with more teams and more drivers. Each team's got different ways to be deranged, right? You take these Red Bull drivers and you could put them in the same team as each other, or you could send them off to the other team. This feels a little bit like in between seasons of Formula One, some of the drivers change teams, and sometimes it's like this. Tracking the derangements is pretty weird. Drivers changing within the team doesn't count, right? Because they're still driving for Mercedes or whatever. Okay. With more teams and more drivers, it gets really complicated. With, I think, this many teams and drivers, it's possible to count them, so maybe I could set this as a kind of fun problem. There's a little bit of ambiguity here that that I should address. Some people count it differently if I send Max Verstappen and Max Verstappen and Sergio Perez. If I send them to Ferraris, if I send one to Ferrari and one to Aston Martin, does that count as the same derangement or a different derangement? Hang on, let's just set one up, there we go. Now they're deranged. If I send Max Verstappen to Ferrari and I send Sergio Perez to Aston Martin, is that the same or different to if I'd allocated them the other way around? It kind of looks quite similar on the page, so maybe I should count those as the same. That's a kind of uniform amount of overcounting, so it's sort of just a technicality about how we count it. Some sort of matrix. Oh, sorry, suggestions in chat. Every driver can go to every other car, bar one. Yeah, the problem is that the things interact. The drivers interact a little bit as we're going on. Let's line them up and get ready to derange them. Each driver can go to sort of n-1 cars, but they interact in a really weird way. Let me show you. So let's put the first driver, let's say they go to here, then maybe this guy, there's already, he's got this choice of, I guess, n-3 cars. He can't drive for the same team that matches, he can't drive for his team. I guess he can't go in this one because it's already taken. He could go in this car. But then it sort of matters where I put him. If I put him here, then the green drivers both have to go over here. But if I put him here, then the green drivers, oh gosh, can they do something different? No, they have to split up. Gosh, maybe this wasn't great. Maybe this wasn't the example I wanted. It's slightly different about how many possibilities there are. Is it 2 in both cases? It's sort of 3. The green driver could go here, or here, or here. Whereas if I put both in the same team, then it kind of has to go here or here. Yeah, okay, that's different. Pick a green driver. Has he got 3 positions he could sit in, or has he got only 2? It depends whether the Red Bull drivers took up all of the Ferrari seats or not. Some of the driver market shenanigans have affected later driver market shenanigans going on. Derangement formula for 6, and then subtracting. Oh, that's a good strategy. Subtract the ways of having people in the same team swapping. Yeah, I think that way of thinking, I've tried to make this work. That was the original plan for today's live stream, but I haven't made it work. That seems like a good way of doing it. It's very complicated. There's some interesting problems where some of the drivers swap, but there's also kind of a problem where the drivers just moved to the wrong car. Like they haven't quite swapped, they've just moved so that Max Verstappen's gone to Sergio Perez's car. That's sort of annoying that it's not quite just a swap that I can subtract. There's all these other possibilities where there's a Red Bull driver on the loose somewhere else. The subtraction's not quite as clean as I wanted it to be, which is why that's not today's live stream. Anyway, the answer to the problem is using the just brilliant formula. It's e to the minus x squared minus 4x plus 2 to the power of 10 dx for 10 teams. At the moment there are 10 teams in Formula 1. This is mad. This is based on the second Laguerre polynomial. This is the answer to the version of the problem that I wanted to know. And it's one of those delights of knowing a bit of mathematics, is that you come up against these problems where probably someone's done it before, and you get to find their answer, go and do the research and find their answer. And sometimes the answer is just amazing, and definitely worth the time looking it up. This is the following number, by the way. So I didn't do this integral, I gave this integral to Wolfram Alpha and got Wolfram Alpha to do this integral. Then I wrote it down on a small piece of paper over here, and oh my goodness, my handwriting is awful. I think I got this. There we go. It's quite a few. This is the number of ways that Formula 1 could derange the drivers, that everyone's driving for someone else. I'm not sure what's more interesting, really, that the derangement problem is the same as this integral, which we only know because some guy happens to work on a pure maths problem as a teenager and an applied maths problem as a research mathematician with the same answer. Or if it's more interesting that this integral is equal to this number, which doesn't look believable at all. Or is it more interesting that the number is equal to the derangement problem? They're kind of all the same. So one way around or the other. What are Laguerre polynomials? That's a really good question, which I'm not going to answer now. They're defined recursively. You can define them recursively. You can define them as the solution to a particular differential equation. I'm not really set up to dive in. Sometimes in applied maths we're interested in differential equations, and the same differential equations have a habit of turning up in different places. I guess that tells you there's not that many different differential equations, maybe? Whatever. Sometimes the same differential equation turns up in different places. When it does, it's helpful to have a name for the solutions to that differential equation, so that every time it turns up, you have like you can recognise it and talk about this one again with these solutions. Is the paper easy to read? No, it's hard to read. The paper is unfortunately hard to read. My experimental plan for the last 5 minutes was going to be to try and read the paper together, but I think that might be a mistake. How's the integral done? Oh, so the integral from 0 to infinity. Yeah, so different ways to define it. A good way to define it is to just put a large number here, like 100, do the integral in the kind of normal way, use some sort of like area under the curve kind of way, and then see what happens if you replace that with 1,000 instead. Did it change the thing? Not very much. Did you put in 1,000,000 instead? The thing is, because of this e to the x inside here, the function looks like, the function looks like this. That it gets very close to 0, so the area under the curve over here is very, very small, and it doesn't really matter. So you can stop at 100 and it's kind of fine. How do you get an actual whole number out as the exact answer? That's a different question. It's the area under the curve, but the area gets very, very narrow very quickly, so it's fine. You can go all the way to infinity. What writing tablet am I using? I'm using a cheap writing tablet that I got on the internet. The brand, it feels fair to do a brand shout out. I don't know if this brand is available anymore, but at the time I bought this, it's got a 5-letter word on it with 2 K's and a V, so probably worth a lot of points in Scrabble. It's all right. It's one of those styles where it's not got a screen, it's just a bit of plastic that's plugged into my computer. Would I do this as a math or interview question? No, gosh, this is way too hard. The derangement stuff with the lemons and limes and the counting stuff, maybe. I could walk someone through some of this in an interview setting, I think. Would I do this? No, definitely not. This is way too hard. The recursion relation stuff is way too hard. Part of the point of Math Club here is we can do stuff that's more fun than interviews, or more fun than math questions. And that involves doing maths that's sometimes a bit harder, or just showing you harder. So that difficult integral, it's kind of accessible, it's kind of alright. So the way you would actually do this, if you had to do this by hand, which I do not recommend doing, you would use a technique called integration by parts. Integration by parts lets you turn it into, after some work, a horrible number that I'm not going to tell you, plus something multiplied, something horrible coefficient here, times the integral from 0 to infinity of e to the x, 4x plus 2 to the power of 9 dx, which is horrible. It's loads of work. It's a technique that you learn at some point in A level to turn this integral into a slightly different one. There's a number out here. But you see, you've turned the 10 into a 9 now, and then you do it again 9 more times, and this is way too hard for A level. It's also too boring for A level. The answer is huge. This is a sort of joke, right? The answer is just enormous number. Title of paper in chat: derangements and Laguerre polynomials. Let's try and get that in chat. Maybe someone helpful will type it for me. That choosing boxes puzzle, to go back to it, I also think it's n-2. I haven't proved it, but I reckon that it's n-2 boxes you've got to look in. And I think someone put in chat the list of 9 things. Good, what else is in here? Will interviews be online or in person? Haven't decided yet. Or in the university hasn't decided yet. We'll make an announcement over the summer. Sorry for the delay. Either way, maths questions. Is it rather accessible? Sorry, I should have read your question out more. Is it accessible? It's obviously horrible. It's really horrible, look. Really, really nasty. Is somebody writing it in chat? Shall I go and write it in chat? How do I get into chat? Oh, I have to be careful. Repeated integration by parts is pretty bad. I'll post it in chat. Okay, I've got it here. I think I got this off. Where did I get this? I can't remember where I got this. I think I got this in. I think I got it off Google Scholar and I think off an author's website at some point, or maybe I downloaded a copy of it. Not obvious whether I've got permission to show you this, but I have now. And hey, it's from 1974. And it's really cool. Good, okay. It's about 6:30, so I think we're going to call it there more or less. Thank you for joining in. Thanks for the questions all the way through. Is there a website where you find math papers? There are 2. Well, sort of one very specific and one very general. So archive, which is spelled like this, It's coming in chat. And authors' personal websites. For example, I think so. I think these, because it's from the 70s, I don't think these guys have got websites with the papers on. But there is this website called Archive, spelled like that, which is a sort of record of where people put papers without formatting, without journal formatting, before they've been accepted. So it's before they've been peer reviewed. It's called preprint, which means sometimes there's mistakes, sometimes things aren't right, sometimes new versions come out, but it's the way that mathematicians share things straight away. You can release the rest of that unseen math paper in a few years, or can I FOI request it? Oh, okay, don't do the FOI request. I mean, you're legally entitled to do an FOI request. I will release it, sure. Okay. It was a while ago. Unseen math. Oh yeah, we used one question. Lots of the questions weren't very interesting. That's the main reason I haven't released it, because it would be work to release it, and lots of the questions were not that interesting. It's 10 short questions, so no long questions. What hour did this live start? We started at 5 o'clock. Sorry, it used to be 4:30, it was sometimes 4, it was 5 o'clock UK time. Daylight saving time happened recently, which is confusing, I know. And we do about an hour and a half. I think I'm going to call it that. We've got some homework, which is like counting the derangements on these cars. Might be a fun thing to try. Counting the derangements on these 4 things, checking it really is 9. Maybe trying 5 things and seeing if that's good or not. Some sort of inclusion-exclusion thing. Can you make this work? Gosh, the Venn diagrams, they'll be in the further reading on the website. Website link in the description and on screen. And gosh, how many boxes do you actually need to look in if all the labels are wrong on n boxes? I think there's enough things to keep people busy for a bit. And we'll see you in about a week's time for another episode of the Oxford Online Maths Club at 5 PM UK time next Thursday. Take care.